The first talk of the morning will be given by Andras Kilian. He's going to tell us about techniques for Hamiltonian simulation and beyond.
Thank you. So in this talk, I would like to tell you about some techniques for Hamiltonian simulation. And my aim is to get you up to speed up to like 2 years ago, which sounds like a reasonable thing, right? Not in Hamiltonian simulation. We will need one more talk to get up to speed as of today. But basically, hopefully at the end of this talk, you will know the main ideas and the main results up to 2 years ago. All right. So I learned at my school, Caltech, that it's always good to start with a quote from Feynman. So Feynman said that simulation is important, and who can argue with a Nobel laureate? So let's do Hamiltonian simulation. And simulation is a good stimulation, it turns out. Indeed, thinking about simulating systems of quantum mechanical systems, which is like probably the most well-fitting problem for a quantum computer, you can argue about that, turns out to be actually a challenging task a little bit. As you see, there was a lot of effort going into developing better and better algorithms. And as you progress, actually what you learn is super useful. You can construct many, many algorithms based on the insights that you gain from Hamiltonian simulation. So I will also hint at some applications. I tell you some development on the simulation side, and hint at what other applications we got from this on the algorithm side. So this is really a broadly applicable primitive. So if you're coming from chemistry or physics, it's a very natural question. If you come from computer science, then you may say, well, it's Hamiltonians, I never attended physics, so it's why should I care? Well, you should care because you can construct very efficient quantum algorithms based on Hamiltonian simulation. So it's really useful for computer scientists as well. Okay, so what's the basic problem? The basic problem is that we want to evolve the system according to rules of quantum mechanics, and that is described by Schrödinger's equation. And for the physicist, I just put h bar equals 1 for simplicity. And then we have this neat equation that the state, the time derivative of the state is proportional to the Hamiltonian, which is a Hermitian matrix describing the energy of the system. And this is just a linear differential equation. Everyone knows how to solve it from calculus 1.101. You can just exponentiate this matrix, and that's how you get the time evolution. So this is really the simplest case, because in more general situations you might have a time-dependent Hamiltonian where somehow the energy and the interactions in your system change over time, and there is work on that. But for simplicity, I will talk about the time-independent case, and Nathan will hopefully cover a little bit about the time-dependent case. Actually, when I gave this talk to some physicist audience, I ran into this question once, that they were truly puzzled by this. So wait, am I trying to solve Hamiltonian simulation using a quantum computer? So they should solve Hamiltonian simulation to build a quantum computer for me to solve the Hamiltonian simulation problem afterwards. Right? They work super hard to simulate their Hamiltonians, and what I am going to use, I'm going to simulate another Hamiltonian. Why does it make sense? Well, it makes sense because we're working like a circuit model, and then you only need to implement 2 or 3 specific quantum gates. Only focus on making these CNOT gate, and I don't know, Hadamard, and I don't know, maybe a phase rotation gate. Just make those super precise. And out of these very basic primitives, you can build up basically generic Hamiltonians and up to very high precision. So that's how it makes sense to use a device and solve Hamiltonian simulation super precisely, and then use a device to solve Hamiltonian simulations once again. It's not a contradiction. Okay. So the first step into this Hamiltonian simulation problem was made by Seth Lloyd in 96, and so he considered a physically well-motivated case when your Hamiltonian is a sum of local terms, and each local term acts on a few qubits, say 2 qubits, just for simplicity, and many spin systems and other systems look like this. So this is a physically relevant model because in many cases the interaction is only between a limited number of particles, and then it's like somehow the whole system just builds up from interactions of individual particles, and then the corresponding Hamiltonian will be a local Hamiltonian. So it's really a physically well-motivated model. And while for the discussion here, I just assume without loss of generality that the Hamiltonian terms have bounded norm. You can always rescale those, so it really doesn't change the problem. It's just easier to talk about the error, and I don't need to worry about the norms. Okay, so this is the idea about doing the Hamiltonian simulation with these local Hamiltonians. So the idea is that you will start, instead of doing in one go time evolution by time t, you will just do a very short time evolution with like t over s, a small time step, and then do it many times. So it doesn't seem very useful at the first time, but then you realize that somehow this small time step, there it's not really important that I have a sum of Hamiltonian terms. I can just, instead of evolving a system with a sum of Hamiltonians, I can just strobostoch, so I can just like one by one evolve with the terms, and then with a short time. And it turns out that in this case, the error that I pick up is somehow quadratic in terms of the evolution time. So as I shrink the time steps, my error decreases like quadratically, and then eventually I get a more and more precise algorithm after repetitions. So in particular, because of this quadratic nature, it turns out that if you evolve, if you take like tk square over epsilon many slices, and you do time evolution with that many slices, then you can get an epsilon approximate guarantee at the end. And so k was here the number of terms. And it's easy to see that in the worst case, this k is necessary, because you can just have, maybe you can have a very stupid local Hamiltonian, which is just the same term k times. And that's basically just multiplying the Hamiltonian by k, or like multiplying time by k. And then, you cannot speed up it. So it's kind of, in that stupid example, k is kind of absorbed into t. So really, you see that in the worst case, t and k match. But we will see that in many physical situations where you have like much more like well-distributed Hamiltonians, local Hamiltonians, maybe local on the grid, this will actually be less pessimistic. Okay, and so I just wanted to quickly like describe why do you have this this formula, why does it work. So basically, you just need to consider the Taylor series for this, and look at what happens for two terms. So I just first describe what happens if you evolve with a sum of two terms. Then just substituting to the Taylor series, I get identity plus some linear term, a quadratic term, and something third order. And now let's look at what happens if I evolve for time delta with one Hamiltonian and for time delta with the other Hamiltonian. Well, in that case, I just plug in the Taylor formula, the first Hamiltonian, the second, and also ignore third order terms. And as you can see, somehow the linear terms will match, and the quadratic terms will differ only a little bit. So here I have h1 plus h2 squared. So I will have in the cross terms like h1, h2, and h2, h1 terms. And if the two Hamiltonians don't commute, then it doesn't matter which order I multiply them. However, in the second situation, only like h1, h2 term appears. So if I take the difference, then somehow h1, h2 minus h2, h1 appears as the quadratic term. So this will be the difference between the two formulas. And so I see that up to first order, the two are indeed the same, and that's why I get this quadratic error. And also, it gives some insight what is the magnitude of the quadratic error, and it's proportional to the commutator. And yes, so this tells me that if and this kind of generalizes to many more terms. So if I have many terms, then somehow the quadratic order term, error term, will depend on the average magnitude of the commutators, loosely speaking. And that's why when I have a system which is maybe local in a spatial grid, then like most local terms will actually talk about different qubits and they will fully commute. And then I can get much better bounds. So let's look at the second order formula. And this is very similar to the first order one. And now I'm telling you the general case, what happens if you have many terms. You just take in one order small evolutions with the individual terms, and then again you do evolutions, but now with reversed order. And this is a nice symmetric formula, and it turns out that it's much better to use this than the first order, because now it have only cubic error terms. And actually, so in the early times, it was not so clear how you can get to a higher order formula. So there was a business, I don't know, in the 60s, you could publish a paper with a sixth order formula. In the 70s, you could publish a paper with a seventh order formula. And the 80s, well, in the 70s, Suzuki came and gave a generic way to how to construct a 2R order formula. And then you could no longer publish a paper of an 8th order. And then quantum computers came, and people picked up this as a practical tool. And so let's look at the complexity of these formulas. Somehow, as you recurse, you need to have more and more terms, and these formulas will look more and more complicated. And in general, an mth order Trotter-Suzuki formula will correspond to like a runtime, like how many times you need to evolve within individual terms, which looks like this. So it approaches linear in terms of t and the number of terms, and somehow the dependence on the extra dependence on the time and the epsilon will be decreasing. But on the other hand, you will pick up a constant, but to an exponentially large constant. So therefore, in practice, people don't really go above like 2 or 4 order formulas, and these are the ones that are used in practice mostly. And as I told you, if the commutators are kind of small, then this k thing kind of disappears, and then you have a better scaling. So this is what you have this is what you can hope for formulas which contain more commuting terms. Yes. Okay, so this is what I wanted to tell you about Trotter-Suzuki formula, and now I will tell you about a related problem, which is now leading us to an application and uses the same ideas, but it starts from a very different standing point. So what happens if I have copies of a density operator? The density operator is a Hermitian matrix. So in principle, I can do Hamiltonian simulation with it. I can just say evolve for time t with the Hamiltonian, which is just plug in there this density operator. But the catch is that I only have copies of this density operator. So I want to implement this unitary map, but now with a very restricted input model. What can I do? And it turns out that you can solve this problem with only t square over epsilon copies from rho. And you don't need to have any knowledge about this state. You just need to have copies of it. And in fact, you can also kind of request copies online. You don't need to store them at the same time. In information theory, it often happens that like the optimal measurement is given by some very complicated permutation over all copies. And this is actually not like that. It's an efficient scheme. So this scheme is due to Lloyd, Mosseni, and Ravenscroft from 2014. And so the idea was that let's look at what happens to a density operator sigma if I evolve with this other density operator, but as a Hamiltonian evolution. So you can just expand this series as a perturbation sequence or a Taylor series, and then you can see that well, in the first in the 0th order sigma doesn't change. Then there is some change proportional to the commutator of the two density operators, and there are some higher order terms. So again, the strategy is that let's go for a small time step and try to reproduce the first order. So the idea here is that now you want to evolve for a very small time step delta, and then what you do is you take your sigma and your rho and you apply an infinitesimal swap. So this S is a swap gate, and you just take a very small amount of swap. And if you do this tiny amount of swapping, then in first order, you get back the commutator in the evolution, and you only have second order terms. So up to second order, we matched the time evolution that we wanted to see. And then again, choosing the right amount of like time steps that you want to do, you can optimize it. And by choosing the time step epsilon over t, then you can see that the overall evolution is like t squared over epsilon. And here you might wonder that, okay, but here we only used each copy for evolving once, and then we kind of throw away. So for every time step, we request a new copy. But maybe there is a better way. Maybe there is a way to somehow reuse this copy a few more times, and then I can do this simulation a bit more efficiently. But it turns out to be that this is actually an optimal protocol, and this was analyzed and showed by Kimmel, Lin, Loh, Ozols, and Yoder. So this is really an optimal procedure. And so why is it useful? Like Seth and company constructed this algorithm for basically doing some very efficient means of tomography on the density operator. If the density operator has large dimension, then like doing tomography is like really expensive. It's proportional to the dimension of the state. But what happens if you only want to figure out, say, the largest eigenvalues of this system? Well, then what you could do is just take one copy of the density operator and do time evolution, do some kind of phase estimation, and then you will figure out what is the spectrum of rho, at least the higher end of the spectrum. And now you can do it with like this clever Hamiltonian simulation where you don't need to run the usual tomography tools, which are like too expensive for you. And indeed, after you do Hamiltonian simulation, phase estimation, you can basically like sample from the eigen basis of your density operator, and they use it to devise some like data analysis algorithms and other things. Okay, so this was one application along the lines of this trotterization, and I want to move to more efficient schemes, which are, well, arguably more efficient. We will see about that. So now I will move to the sparse case. So it's a more general setting. Now we only require that the Hamiltonians that we want to simulate are sparse. And there was a line of work, really a long line of work, to improve the complexity of this problem. In particular, like almost optimal complexity was obtained by Barry, Childs, and Kotai in 2015. And up to logarithmic terms, they got this scaling, which is the time that you want to evolve, the maximum non-zero element in your Hamiltonian matrix, and the sparsity. And there are some logarithmic terms in the precision and other things. And, and just 1 year later, Loh and Chuang actually showed what's the optimal complexity in this model. And now there are no hidden logarithmic factors. It's just really the same term as before, but now only additive terms in terms of log 1 over epsilon. And so this is actually an optimal scheme, and the optimality, so the lower bound, I believe, was proven by these authors, or maybe these authors in another paper. But the lower bound comes from some query problem, and the upper bound is really a Hamiltonian simulation techniques. And so now in this model, we really solved Hamiltonian simulation. We know the optimal complexity. And so now you can see that we have really logarithmic dependence on the error, and it's additive. And previously with Trotter formulas, we either had some like high polynomial dependence on the precision and some like small constant, or like a very like exponential constant plus some small dependence on the error. So it seems that this algorithm is strictly better than those. And then there was a recent survey from 2018 QIP by Child, Maslow, Nam, Ross, and Su. And then they actually like looked at these algorithms, and it turned out that indeed, in theory, in the order I presented the algorithms, the latest algorithm is the best. It turns out that Trotter actually makes coming back, and then turns out to beat the other algorithms in practice. So it turns out that the derived upper bounds, like how many terms you need to apply and how frequently, these are loose bounds. Actually, in practice, when you have like spatially local Hamiltonians on a lattice or something, then really these commutators are really nice, and somehow they end up canceling each other, but we didn't really have a good handle on it. So the theory and the practice was very far apart, and it turned out that Trotter is the best method if you just really want to have some reasonable like system size, Hamiltonians, and reasonable precision abound. Then it turns out that actually the best method is to use Trotter, like a low-order Trotter formula. And so this really like urged people to work on this, to figure out why are the bounds so loose. And then Earl Campbell had a nice result when he kind of showed like an average case, worst case reduction in some sense. So maybe the problem is that in Trotter, we fix an ordering of the local terms and then we evolve with this. And maybe it's a very good algorithm. Typically, like for most input state, it actually works very well. But you know, we have like a worst case bound here, so maybe there is some tiny corner of the Hilbert space where this is actually breaking down a little bit. So what can we do? It's like, as an analog, I would like to draw a parallel here with like the Dye-Jose algorithm. The Dye-Jose algorithm is like the deterministic complexity. You need to read through the whole string to figure out if it's a balanced string or constant. But if you randomize it, and if you can look at random places, then it's much easier to figure out if it's a balanced versus a constant function. So maybe, you know, if I have a fixed instance, then maybe let's randomize the trotterization that I take, and then I avoid these nasty corners because I just randomize them out. And it turns out that indeed this analysis works nicely, and he could improve the trotterization error bounds by just considering a random sequence of small evolution times. And but there was still a large gap between what we saw in practice and what was the bound in this analytically analyzed case, and Nathan will talk about this a little bit more.
So the randomness support is on the order of the local terms or something?
Yes. Okay. Yes. You define some kind of sampling procedure when you define how you should sample local terms. You randomly sample them. That will be your simulation algorithm. You just apply the local terms in that order, and then it kind of like averages out the places these nasty potential states at the random position, probably far apart from your actual input state. But it's also possible that you can analyze this algorithm better, just we don't know how to analyze the deterministic situation, so it's really not fully understand what's going on. But randomization helps, and there are other techniques by Nathan. Okay, and well, now I already told you one optimal algorithm, and I tell you another better algorithm, which is optimal for the same problem. So how can it be? Well, what is your figure of merit? So this is a result by Lowe from last year, and then it turns out that if you don't look at this kind of norm of the Hamiltonian matrix, then maybe look at this norm, which is the maximum row norm of the matrix, then you can do better. And in the worst case, somehow the product of this like maximal row norm times square root s can actually match this term, but in many situations it's hopefully better. So it's if your figure of merit is this norm of the Hamiltonian, which is a nicer norm to work with, then it turns out that you can get a square root of sparsity here. And as I told you, Hamiltonian simulation used in many algorithms. For example, the famous HH algorithm is just using Hamiltonian simulation as like its core primitive, and it had a linear dependence on sparsity. Now you just come, look at this new algorithm by Lowe, plug it into your favorite HHL version, and now you get a square root dependence on the sparsity, and now you depend on the maximum row norm of the Hamiltonian matrix.
So what's the epsilon dependence?
Well, it's something, it's little O1, so it kind of goes to 0, but not as quick as you would like.
So bigger than log 1 over epsilon, but smaller than 1 over epsilon.
Well, I guess, yes. I don't know. It's a bit hard to do this like exponential to the log on the spot, but anyway, the message is that it can be arbitrarily small.
I believe that the scaling ends up going something like e to the square root log 1 over epsilon, if I recall. So it's in between polylogarithmic and polynomial.
I'm not entirely sure. Okay, I think, but that doesn't justify this notation. Whatever. So okay, let me just tell you that this algorithm is like very nice in theory, and you don't want to use it. So this is a very nice algorithm. You can do these complexities, but if you now return to like reality land and you want to apply your favorite Hamilton simulation, just use Trotter. Don't use this. Or like, well, you can't use Trotter because it's sparse, but use, I don't know, the signal processing version, the previous one. Okay. So I would like to shed a bit of light on how these methods work. So under the hood, they use a thing called block encoding. So and this is a tool to represent a matrix, which is a non-unitary matrix, but you want to work with on a quantum computer. So think about this A as your Hamiltonian, and you want to somehow implant this Hamiltonian to a quantum circuit where the unitary matrix is the top left corner A, and you don't care what's here. That's totally irrelevant. So really just the top left corner, which is like start with 0 state, post-select on 0 state. It's kind of like you can imagine that this is like a probabilistic implementation of the linear transformation A. When if you start with all zeros and post-select on the all 0 state, then you implemented this linear transformation. So I just show you a quick construction how you can implant a sparse matrix into unitary this way. So now assume that all matrix elements are at most 1. And then we need sparse access to the matrix, which means that we need to be able to compute the location of the non-zero elements efficiently, and we need to be able to compute the value at these non-zero entries. It's a little bit like a adjacency least access to a graph, for example. So what you end up doing, you only need to prepare like row states. That's why I call this matrix unitary row, which like given a row index I, it prepares a superposition over indices k, which correspond to non-zero entries with like corresponding amplitudes, and the amplitude should be roughly the square root of the matrix element, and there is subnormalization factor to make this state at most norm 1. And because this state can have norm less than 1, you add the garbage register, and then you map, you kind of show that it's a garbage, and this is a flag qubit indicating that you have garbage there. You also need a column unitary, which prepares column states. So given a column index j, it creates a superposition over row indices L, such that these are non-zero matrix elements. And again, you get a similar state, but now you mark your garbage with a different label. And so the block encoding of A over S is the following. You just take R dagger C, and I show you that it's a block encoding, just like, so it's a block encoding. I only consider the things where I start with all 0 and end up with all 0, and I would like to scan what is the ij element of this top left corner, and I will show you that this is indeed aij over some constant, some number. And so I can rewrite this inner product as I just regroup this dagger term as like the R operator applied to the I state and the C operator applied to the J state. And then, well, I just plug in what was the definition, and I observe that the garbage state was marked with a 1 here and a 2 here, so in the inner product they just disappear. They are not there, so I can only consider the main part of the state. And now this is some state where it corresponds to the ith row, and this to the jth column. So the only overlap between them, and it's ij and it's ij. So that's the only thing that doesn't cancel. And indeed, if I take the product of square root aij by square root aij, I get aij. And then I had this normalization factor by square root s, so I get a subnormalized version of the matrix. So the ijth matrix element is indeed aij over s. I have a block encoding of the matrix divided by the sparsity. Yes, and now I show you why a block encoding is very useful in this situation, and I will demonstrate it using quantum walk operator. So now I assume that the matrix is actually a Hamiltonian, a Hermitian matrix, and I also assume that U square is an identity matrix, and Low and Wiebe, sorry, it should be Low and Schwang. Sorry, it's paper in Low and Schwang, and they showed that that you can basically, without loss of originality, assume that U is such a matrix. You can just do some small trick to, if you would have a different unitary, just do a small trick and you will end up with such a unitary. So I can assume that for free. And I define a Szegedi walk operator as just apply the block encoding and then a reflection. So what does it do? If you start with the all zero states, then basically don't do anything. And if you don't start with an all zero state in the first registers, then apply a minus phase. So it's just a reflection around states starting with all zeros. And now I try to tell you the intuition behind this Szegedi walk operator. And this understanding really comes from Andrew Childs and then later, again, Low and Schwang. I'm sorry for the typo. So I was really preparing for Nathan's talk in this talk, so I was fixated on his name. OK. So what is the claim? That if you just apply k times this walk operator, then top left corner will be just the Hamiltonian matrix, but transformed by a Chebyshev polynomial, the kth Chebyshev polynomial. And here's just a quick recap. The kth Chebyshev polynomial is defined as the cosine of k times arc cosine x, and surprise, this is a polynomial of degree k, although it's not apparent from this formulation. And this can be checked by checking this recurrence relation that the k plus 1 Chebyshev polynomial is really just 2x times the one smaller one minus the 2 smaller one Chebyshev polynomial. And we will use this in the proof. So I prove this claim about the Szegedi walk operator by induction. And observe that if I take the 0th power here, then it's just identity matrix. So the top left corner of the identity matrix is the identity matrix. So T0H is indeed the identity matrix, and so it matches the claim. What happens if I take only like one W here? Then it's just the top left corner of W, and that's indeed H because it was a block encoding of H. So really, my induction can kick off. And now I show you the inductive step. So now suppose I prove the claim for W to the K. So now look at W to the K plus 1. And I just write the first W term out. And then here is the rest of it. And then, well, I kind of observe that this term is just, so I distribute the term with this minus sign. With the minus identity, I just get this term, which is here U times W to the K, but observe that U was self-inverse. So it kind of cancels this first term here, and it just makes U times W to the K will be basically W to the K minus 1. And for that, we know that the top left corner is just the K minus 1 Chebyshev polynomial. And for the other term, I kind of take this term, and it's a projector, so I can take its square, and it's the same. So I kind of pull out one projector to the left, one to the right. And this is just telling me about the top left corner of U, which is H, and there's a factor to it. So 2H. And here I can have the top left corner of now the kth power of W, and that by induction is just the kth Chebyshev polynomial. If I multiply these matrices, then I just end up seeing the recurrence relation for Chebyshev polynomials. So I am done. I prove this claim by induction. OK, so this is just a slick proof of this. And this is called a walk operator. And this is very useful in our applications. So one way to leverage these Chebyshev polynomials is to take linear combinations of those. So the linear combination of unitary trick is the following. Suppose that I have some unitary matrices from V1 to Vm, and I want to take linear combination of those, which is a linear operator. And I can prepare a quantum state A, which is the square roots of the coefficients normalized. So it turns out if you have a fancy unitary which given register I applies the ith of my unitaries, and I just apply a state on the left and the right, then this will just really, these square roots just meet each other, and then it will be just a linear combination of these terms, and you end up seeing the linear combination operator that you wanted, but subnormalized with the one norm of the coefficients but due to normalization. So in particular, if you have these all operators are like Chebyshev polynomials of order k, then you can implement this fancy unitary which looks a little bit like scary as the following. You just take a binary decomposition of the first register, and on the first binary controlled on the first binary digit, you apply the Volk operator. Controlled on the second, you apply it twice, and so on, 2 to the n-1 at the end. And so if you just look at this matrix, it applies this fancy controlled evolution by the first register, and it's a very simple circuit. And now you can take linear combinations of these W powers. And in particular, if you take linear combination of unitaries, the top left corner is also a linear combination of the top left corners. So now you can take linear combinations of Chebyshev polynomials of the Hamiltonian that you had. And so now the idea is that you wanted to implement Hamiltonian simulation, which is just applying this e to the itx function. You decompose it as approximately as a sum of Chebyshev polynomials. And if you have a good approximation, then you can just plug in matrices. So e to the ith is roughly a linear combination of quantum Volk steps. At least the top left corner of this matrix will be linear combination of the Chebyshev polynomials, which again, just giving you a good approximation of the time evolution here. So here, I told you that you need to subnormalize this top left corner by the one norm of the coefficients. So here is one good news, that you actually don't need to do these quantum Volk steps up to a very high power. So it means how many times you need to apply, what's the maximal time you need to apply your quantum Volk, and that's not very high. It's like sparsity times time plus log 1 over epsilon. That's very nice. The bad news is that if you increase time, actually this subnormalization factor is really bad. It's exponentially bad. So how can you get around it? And the way to get around this is to do small steps. And then for small steps, actually, you don't have very bad subnormalization factor, and hope that you can repeat it many times. But the problem is that even if you just do small steps, all these like subnormalization factors will multiply exponentially, and if you apply these amplitude amplification tricks, things chain together badly, and you get an exponential runtime at the end. And you know, here the problem is that really in every time in amplitude amplification, you need to reflect over the initial state of this particular algorithm piece that you have, and that uses all the previous preparation methods. So in every time, maybe you apply it twice more, and then you end up with an exponential algorithm. So the way around is the following. It's called oblivious amplitude amplification, where, so this is the situation here. I have a target unitary V, and I can implement the block encoding of not V, but P times V. So it's really like a faulty or like a stochastic implementation of the matrix, where with probability P, I succeed to implement this unitary transformation, and it's marked by some ancilla qubits. And with probability 1 minus P, I just get out something really, I don't know what I get out. So I want to boost this to a proper implementation of the unitary, where I had the V in the top left corner. And it turns out that you can do it, and you don't need to consider at all the input state. You can just boost this success probability here by using the amplitude amplification circuit, and it just works. Yeah, there is more intuition behind this, but basically just use, because it's a unitary matrix and it kind of doesn't matter what the input state, it always gets the same subnormalization factor. You can just apply the Grover circuit without actually caring about the initial state, and that's why it's called oblivious, because it doesn't care about the input state. And now you kind of improve the success probability of your algorithm, and now you can just repeat for small time steps the algorithm, and now you don't have this chaining problem any longer, because each individual step is actually pretty good itself. So this is how they came to this very efficient algorithm. And yeah, the key is not to reflect about the initial state. And now there was another improvement over this, and I just want to show you what's the algorithm that we have at hand. So we take linear combination of Szegedi-Volk steps, and the Szegedi-Volk step is really just apply unitary reflection, unitary reflection. This is your algorithm, and we take this for different time step, for different lengths, and then we take linear combinations. But what if we do a different version? We don't combine different time steps, but just do time steps differently. So what I do here is, instead of doing a reflection operator, I apply a different phase for the 0 state and the others. So like previously my spectrum was plus minus 1, it was a reflection operator. Now it will be something which has a spectrum is e to the I phi 1 and minus 1. So I just add the phase there. And maybe apply different phase in every step. And it turns out that if you do this, then you can basically solve this Hamiltonian simulation problem with a fixed length of circuit. You don't need to combine different runs, and that's a very nice feature. And this is basically by analyzing and understanding this circuit, which was proposed like 15 years ago, but no one knew how to handle this situation, Low and Chuang can actually analyze this and derive an optimal Hamiltonian simulation algorithm which has this form. And so I am ignoring some slight details here. Maybe the circuit doesn't exactly look like this, but almost looks like this. Okay. And so here it looks very nice. It seems like the best asymptotic algorithm that we have, but it was suggested that maybe finding the correct angle sequences is super difficult. Like people struggled with the initial algorithms with even going beyond 50, length of 50 a sequence. So that was a big problem with these algorithms. And then Zhang Van Hao showed last year a rigorous bound and showed that actually you can find the angles in polynomial time, but it's still not a polynomial that you would like to see in practice. Like if it's cube, it's like less practical algorithm. And now, just the day before yesterday, there was a very nice paper by Dong, Meng, Brigitta, and Lin. And so they showed how they can find up to 10,000 angles on a laptop. And it's a very nice, simple algorithm based on optimization. So it really seems that probably the bottleneck will not be the angle sequence finding by the quantum computer. So far, classical computers are ahead. Okay, and so here I just wanted to now tell you how to kind of what we learned about algorithms from Hamiltonian simulation. So all these schemes that were developed to find better simulation algorithms kind of lead to this unifying picture of quantum algorithms. So really, if you want to work with some matrices A which are non-unitary, just embed them into a quantum circuit, and the top left corner is really fine to hold any matrix which has norm at most 1. You don't even need to have the same N-Sylla qubits set to 0 at the beginning and the end. And we learned that you can efficiently construct block encodings. For example, if you have a unitary matrix, the top left corner of unitary matrix is just itself. So it's really good. I have a very efficient block encoding for unitary matrices. Well, that's actually used in other simulation algorithms. You can also encode a sparse matrix, as I showed you. You can also somehow encode a matrix which is stored in a quantum RAM in a clever data structure. It's used in machine learning algorithms primarily. And also, if you can prepare a density operator, a purification of it, then you can block encode the density operator. This is like a coherent version of this density matrix exponentiation that I showed you. If you have not only copies of rho, but you have a circuit which prepares a purification, you can much nicer handle these density operators, and you can have a much more logarithmic dependence on the error. So you have much less query complexity in this case for simulation. And you can do other crazy stuff. The nice thing is that once you have block encodings, you can take linear combination of block encodings with the LCU lemma as I showed you. And also, if you have block encodings, just take the corresponding product, and you can with a slight trick, ensure that the top left corner of the product of the block encodings will be just the product of the matrices that you care about. So now you can combine all sorts of models. If you have Hamiltonian, which has some sparsity structure, but also has some non-sparse structure coming from unitaries. You can somehow separately handle the two cases and come up with a combined matrix which has a unitary part and a sparse part. And now you can do Hamiltonian simulation, HHL, all sorts of algorithms using this. And this idea which comes from these phases that you added there actually comes to single value transformation. And so it turns out that what you can do, you can apply a polynomial transformation to the singular values of this block-encoded matrix. And for any polynomial which is bounded and has some nice parity property, you can find corresponding angle sequence now very efficiently as of a day before yesterday. And the nice thing about this algorithm is that it has a very simple circuit. This is the quantum circuit doing this transformation. And well, with this, I would like to end the talk, and I just want to tell you why these results are now outdated. Because in the last year, I list here like 4 very important QIP talks from last year and this year, and they pushed forward the limits of Hamiltonian simulation in various directions. They showed you how you can implement very efficiently time-dependent Hamiltonian simulation, or how you can do some nice chemistry with a reasonable dependence on some orbitals and electronic structure of the problem. And you can also implement very efficiently lattice Hamiltonians and analyze them rigorously using this spatially local structure. These are all from QIP 2019. And this QIP, it's really just a sample of results. You can do well-conditioned multiproduct formulas, which kind of are both best of both worlds, best in terms of analytic convergence guarantees and like precision bounds, and somehow using this hidden commutator structure that Trotter formulas could very well exploit. And there is many more results. It's really just a sample of many results, and Nathan will talk more about this. And there is also a frontier ahead us. How can we simulate more complicated models of Hamilton or like quantum physics, maybe field theories and so on? And it seems that there will be much more results on it, or at least I hope so. Thank you.
We're a bit over time. Maybe we can just have one question if there is one, and then we'll have more time during the panel discussion.
Yes.
I was wondering, when you were talking about Hamiltonian simulation, you said that maybe we don't have to go to all these more complicated tensor or hybridization techniques. We can go back to Trotter, and in practice this should work as well. So is this also true for the application that we talk about, like linear systems or things like that? There, do we need these hybridization techniques, or can we do like simple phase estimation things?
So totalization really exploits this, like it comes from physical intuition, and it kind of applies where to physically motivated systems. So in particular, you can do totalization when your Hamiltonian is really a sum of local terms. So if you happen to have a linear system of equation where it's a sum of local Hamiltonians, then sure, you could probably want to use this as a subroutine. But maybe you have, but in algorithmic application, it's more typical that you have some sparsity structure, some graph or something else. And there, for sparse structures, you don't have this Trotter trick. It only applies to sum of local Hamiltonian terms.
Okay, thanks.